Good afternoon, professors, ladies and gentlemen. I'm a master student Wei-Lin Chen from Taiwan Furen Catholic University. Today, I'm going to introduce my research with you. My topic is Retransformer, a self-attention based model for machine translation. The following is my presentation's outline. First, I'm gonna introduce the background, why I did the research, and how does the model can improve. Second, I will introduce the model structure and how these layers improve the model performance. Third, we use BLE, the common machine translation metric, to prove our state-of-the-art model retransformer can improve the performance of original transformer. Last is the conclusion and our future work. Before this page starts, I want to explain why we call the model retransformer. Retransformer is based on the model transformer. And another reason, we refine the layers and the building blocks of the original transformer, so that's why we call it retransformer. Nowadays, due to the massive, convenient, and fast transportation platforms, frequent communications among people in different countries are really common and drive a deeper need of translation for everyone, anytime and anywhere. Machine translation is also one of the most popular and hardest work in natural language processing. In 2017, Google Brain proposed the multi-head self-attention mechanism, leverage the parallel computing in neural machine translation. Most of researchers improve their model by self-attention at the moment. Although the flourishing of GPU computing allows language models and self-attention mechanism to improve to a certain extent, this situation has caused recent models to be developed in a stacking or larger duration. This model training by larger computing resource can only be owned by certain specific group. After several experiments, we believe that the language model's layer should be modified with each on specific language. For example, when the model is only used to communicate between two people with different native language, the model should be a specific and small one instead of a generalized or large one. In fact, it's not necessary to stack numerous encoder and decoder layers with the English-German and English-French translation model. In this paper, we are committed to tuning the sub-layers in the state-of-the-art model transformer, which can relatively increase the inference rate of the model. To sum up, our proposed method has the following advantages. Inspired by reference 2, we reduce the model parameters. Second, modify the amount of point-wise feed-forward layer combinations immediately after self-attention layer in the encoder layer. We believe that a higher ratio of self-attention layer to feed-forward layer assists the model to understand natural languages. Last, we propose a multi-head self-attention visualization heat map. The heat map based on the attention weights of input sequence. After self-attention mechanism processed, we can analyze the multi-head self-attention where the translation model pays attention to in the sequence through the heat map. This part is our proposed model. First is preprocess. We apply subword tokenization. The method has the ability to process the real words into subword pieces. In the same text dataset, it can reduce the dictionary size to a considerable extent and improve the relationship between affixes. Like the figure shown below, unfriendly can be split to un, F-R-I-E-N-D, friend, L-Y, li. Lower can be split to L-O, low, L-O-W, low, and E-R, With the above method, we also deal with the sparse words in the training set, split the sparse words into subwords, increase the relationship with different words. Second, we think there are some lazy layers in transformer, so let's make some experiment to prove it. We attempt to figure out where the transformer needs so many encoders and decoders in a particular translation dataset. We implement it in various encoder and decoder combinations. The arrangement of combinations we proposed is considered with transformer as the baseline. Finally, the combination of 6-layer encoder and 2-layer decoder comes to be the most efficiency translation model. It can be balanced in training time, inference time, and the number of model parameters. See the table shown below. 2 layers decoder got 30.99 bullet score, and the training time is 0.68 times to the original transformer. Next, we modify the encoder with pointwise feedforward network and self-attention. In the encoder of the original transformer model, as shown in figure A below, after each self-attention layer, there is a pointwise feedforward layer. But in early step, if we apply the nonlinear transform in the encoder, will interfere the self-attention mechanism to understand the important hidden message. Therefore, we try several self-attention and feedforward layer combinations to know the most helpful combinations for translation. Last, we apply 2 self-attention connected by a feedforward layer as our modified encoder in retransformer, like figure B below. To better understand the performance of different combinations of self-attention and feedforward layers, we have made some comparisons of different types of modified encoders. Modified encoders varies the combination of feedforward layer and self-attention layer as shown in table below, where character S and F represent a stack of self-attention layer and feedforward layer respectively. Therefore, a stack of 6 SF, 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 SF represents the baseline of transformer. The first column of the table is original transformer, only got 29.33 bullet score, but our retransformer SSF, SSF, SSF got 32.14. So we think if the encoder is modified, the model performance will be better than transformer. Such a 2-to-1 combination of self-attention and feedforward layers outperforms other combinations and becomes the basic building block of the proposed retransformer. Retransformer N is mainly constructed by the methods mentioned above, where N specifies the number of layers in decoder. Unbalanced encoder and decoder layers are adapted. The encoder are 6 layers and the decoder are 4 or 2 layers to reduce the model parameter and increase the speed of inference. As the result, the proposed retransformer outperforms the original transformer in terms of bullet score and training time. The figure shown below is the building block of retransformer. Next is the experiment part. First is about dataset and some hyperparameters. We use World Machine Translation 2014 English, German, and English, French as training dataset, then use Test 2014 as test set, and apply bullet score as model performance about the machine translation metric. The used optimizer is Adam Optimizer. The varied learning rate formula is demonstrated in the following equation. The page is our experiment result. Retransformer 2 obtains the best bullet score of 32.14 and 55.62 in the World Machine Translation 2014 English, German, and English, French dataset compared with the baseline original transformer. The bullet score is 27.3 and 38.1, which is about 4 and 17 points of bullet score higher. The training time of retransformer 2 is only 0.556 times to the original transformer. In addition, Burfield's transformer requires a longer training time, mainly because BERT is a larger pre-trained model, so if we apply BERT into translation model, we have to wait for the output of BERT. The experiment results reveal the training time of the BERT-fused transformer is around 4 times to the proposed retransformer 2. In order to understand where the attentions of the encoders of different models pay to, the visualized heat maps are demonstrated. The heat map is based on the attention weight of self-attention mechanism from the last encoder. Two sentences from Word Machine Translation 2014 English-German are randomly selected. Sentence 1 is word currency standards have enormous inertia. Sentence 2 is that will not happen soon. In this 2 page is about sentence 1. We can see the original transformer sticks on the start and the end. And start of the symbols is hardly deal with the sentence semantic, but retransformer it can, like currency, standards, and enormous. Then we can see the results from the tables below. From the table of sentence 1, retransformer can focus in correct words. The matched correct word read in transformer and retransformer is 1 and 3. From sentence 2, retransformer has the less bright blocks too. The number of the brightest blocks about original transformer and retransformer is 8 and 8. But second bright blocks is 3 and 2. Third bright blocks is 5 and 3. The less bright block means self-attention mechanism is more focused in these important subwords. With the upper reasons, we think retransformer is outperformed than transformer. Last, let me make the conclusion. Retransformer improves around 4 and 17 points of blur metric against the transformer over the Word Machine Translation 2014 English-German and English-French translation corpus, and the required average training time is around half of transformer. Based on my data, I come out some hypotheses. First, there is no model applies to all machine translation texts. We have to modify the model to fit the language we want the model to translate. Second, stacking more layers of self-attention before feed-forward layer in encoder provides with better comprehension to the original input. Third, reducing self-attention layer for decoder produces better outcomes. And these 2 points will be our future work. We hope to find the correct balance between self-attention and feed-forward layer in the encoder for different language families, and find out the proper decoder to better deal with the original input and the current temporary output. The decoder is mainly generate the target sequence. It should not apply so much such self-attention mechanism to focus on some sequence. So we think to find the new algorithm to be the new decoder is necessary. This is my representation. Thanks for your listening.